Hi, welcome back to part 2 of Riemann and the definite integral. In the last video, we talked about the definite integral itself. Remember, it was written as, the definite integral from the area from a to b under the function f of x. Now, where do we get this all from? Remember, from our video in the last one, this is our length of our rectangle, this is our width of our rectangle. This is an infinitely thin, infinitely small rectangles. Right here. And so the A to B, the domain A to B is the width of the area region that we are looking for. So remember, and the only thing this finds is area. That's its only job, to find area. We're talking about a lot of applications with that. So let's look at some properties of the definite integral. If we always think of this as an area finder, this is not too hard to find. Matter of fact, notice when I said it, we were looking for the area from a to b under our function f of x. So this is saying I'm looking for the area of from a to a under my function. Well, let's just graph something right there. Let's just so there's a. I'm looking at the area underneath this rectangle. That's what I want to find. I want the area of this rectangle. And that's not too hard to get because, well, there's zero width. So the area is just going to be, of course, 0. So the area from A to A is just 0. We have some other rules. We've mentioned this one before. This is the constant rule. I can just factor up the constant. When we did the antiderivatives with u substitution, we always talk about taking that constant out. So I can even multiply by that constant. We get a to b of f of x dx. We can split region. Now this is a very important rule for us. We can split an integral. Or in this case, an area. Man, you did this back in geometry in Algebra 1. Remember when your teacher said, hey, look, you want to find this area of this box right here. And what your teacher would have you do, you'd say, well, I could just cut this off. I call this area 1 and this area 2. We can always break apart different areas. Well, the same thing is true for calculus. We can break areas apart. So I could rewrite this as the area from a to b, f of x dx. Don't forget your dx's on these. Plus or minus the area from a to b, g of x dx. Very simple to do. Now, the next one says we want to go from A to C. Well, this seems kind of weird because everything goes from A to B. What's another letter? What they're really saying is here is, let's say I have a region from A to C, but I have this number B in the middle. Well, I can add this area plus this area to get the total area. So in other words, we're saying the area from A to B of f of x dx plus the area from B to C, f of x dx, is the same as if I take the entire area. Now, this should sound familiar. It should sound a little bit like segment addition postulate from geometry. It's kind of the same concept, except for we're adding areas. Now, this is an interesting one, okay? This is an interesting one. Typically, we always go from A to B, but notice we're going in the opposite direction. Think about our graph. See, we normally go from A to B, but we're starting at B, and now we're going to A. So we're going in the opposite direction. So what that does is it gives us the opposite answer as if we went from A to B. We're going to talk more about this when we get to the fundamental theorem of calculus. We will see this then. This is a really cool rule for us because we can always change signs if we don't like something. We can just rearrange the order in which we find the area. So let's apply these properties, and I promise you this is the easiest, most fun thing you're going to do all year. Sorry, I had trouble zooming. So evaluate the following given the following information. Excuse me. So this says the area from 1 to 9 under our function is -1. Now, a negative area, it does mean something for us. We'll talk more about what it means to have a negative area. It's more like a vector. It's more like a direction. Okay? If you're in physics, you've seen negative areas before. Okay, we'll talk about that. From 7 to 9, the area is 5. And then from 7 to 9 for h of x, be careful, different function, the area is 4. Now for the first one, I am going to show all the work, the tedious work that really goes in here, but your brain is going to do this naturally, so we're not going to ever do this much work. So I'm applying for the first one is one, I obviously can split them, so I can apply my property here where I split the integral, but I also have my constant rule, so for my second one here I can factor out my constants. So for the first one, I'm going to write this as 2, the area from 7 to 9, f of x, dx, really I just want to practice writing dx, minus 3 from the area from 7 to 9, h of x, dx. Now, we'll never write this stuff out again, really, because it just takes too long. So we can just do both of this in our head. The first one says 2. We want the area from 7 to 9 of f of x. They're telling me that area is just 5 minus 3. The area from 7 to 9 of h of x, they're telling me that's 4. And that just becomes 10 minus 12, or negative 2. Again, you can do most of this in your head, okay, which we'll see there later on. All right, for a question like number 2, be careful. They want the area from 9 to 1 of f of x. Well, I don't know 9 to 1, but I do know 1 to 9. This is the one where we switch direction. We're going in the opposite direction. So I'm going to rewrite this. Now, this one I always tend to rewrite. The area is the opposite area from 1 to 9, f of x dx. And that's going to give me negative, and from 1 to 9 is negative 1, and this is number 1, just like your favorite calculus teacher, me. 3 is a little bit tougher. 3 we have to do a little bit of algebra. Okay, from 1 to 7, we want to find the area, but we don't know the area from 1 to 7. We know the area from 1 to 9, and we know the area from 7 to 9. We don't know the area from 1 to 7. But I have the entire area, and I have part of the area. I can just do some math to subtract it. So I can write this as the area. I'm going to use my addition rule right here, my addition property up here, where I can add the different areas together to get the whole area. So I know that the whole area, 1 to 9, f of x dx, is equal to the area from 1 to 7, f of x dx, plus the area from 7 to 9, f of x dx. Man, the AP loves seeing stuff like this. All right, so we're going to get negative 1 equals the area from 1 to 7, f of x dx, plus, well, from 7 to 9, we're told that was just 5. So then I can just solve that. Therefore, the area from 1 to 7, f of x dx just becomes negative 6. Another way to look at this, geometrically, I want 1 to 7, that's my unknown. I know the area from 7 to 9 is negative 1, and I know, whoops, sorry, that's 5, sorry. But the entire region is negative 1. So I can just say, what's that, x plus 5 equals negative 1? X is negative 6. So we can think of this as our segment addition postulate from geometry. I know you all remember that rule, right? I don't think so. All right. So let's take a look at a couple more. We want to evaluate the following, given the following information here. So they're telling us the area under this parabola from 0 to 6 is 72. The area underneath this line is 18. And we can even verify that one. Watch this. We're going to talk about this later on. From 0 to 6, right? What's the height here? 6. Area of a triangle. Area is 1/2 base times height, which is 18. Easy to prove. We're going to talk about that in a few moments. And we're told the area from 0 to 6 over here is 6. That's easy too. This is just, remember, 1 there. So this is the line f of x equals 1. From 0 to 6, well, that's just a rectangle. 1 by 6, which is 6. So we can verify a lot of these. This one, we have to do some math. We have to do what's called the FTC on this one, which we're not old enough for that just yet. But we can apply these if they give us the rules. So for question number 1, they want to find the area of 4 times x from 0 to 6. So which one of these am I going to use? It's not x squared. Oh, there it is, x. So real quickly, I can write this as 4 times the area from 0 to 6, x dx, which is 4 times That's just 18, and that's going to give us 72. Now this one, remember, is a little bit trickier right here, okay, because they switched it on us. So I am going to rewrite this the direction they turned it around from 0 to 6. And I'm going to put my 12 on the outside, and I got dx. 12 is just a constant. Remember, I can factor that out. And when I simplify this, we're going to get negative 12 times from 0 to 6 dx. Oh, that's just 6, and we get negative 72. So the area there would be negative 72. All right, number 3. Let's see here. For this one, this is 2 times x squared minus 3x plus 3. This is the only hard one, by the way. This is the one that's going to cause the most trouble. So I'm going to write this all the way out. This becomes 2 times the area, 0 to 6, x squared dx, minus, I can factor out the 3, 0 to 6, x, plus, I'm going to factor out this 3 here, 3, but I'm left with just dx. See, it's kind of like I'm distributing dx. And that's not bad to do. 2 from 0 to 6, x squared is 72, minus 3, that becomes 18, plus 3, that becomes times 6. And then what do we get here? 2 times 72 minus that. And you get, if you simplify all of this, what's that? You get 108. I'm going to do that for you right there. All right, go to part 3. We're going to take a look at a bunch more examples here. We're going to try to maybe show you some really cool things that you can do with if you understand symmetry.